And now for question 6. So this is an equilibrium question primarily, although there's some other bits later on the rates topic. Again, I've written down all the answers here, and I'm going to scan all this stuff and share with you in due course. But I'll walk you through it here now. Okay, so the reaction quotient and the Kc are really quite similar, but there is one specific difference that you need to know. So the Kc is the expression you're taught probably first when teaching equilibria, which is the ratio of the concentrations of the reactants and products at equilibrium. But the reaction quotient is the same thing, but at any point in time. So just like with this question in question 6, you're told that at the start a load of sulfur dioxide, oxygen and sulfur trioxide are chucked in a pot together. It hasn't yet reached equilibrium, it's just right at the start of the process. And at that point, the number you get when, well, it's down here, that's the reaction quotient, the number you get is at that point in time. Over time, the reaction will reach equilibrium, it will settle down to a position of equilibrium, and then the value you get then, that's Kc. And just following on from that, if you're thinking about Le Chatelier's principle and so on, if you were to change one of the concentrations at equilibrium, the reaction quotient changes, and then the equilibrium shifts in order to sort of regain the equilibrium constant. And that's why the equilibrium position shifts when you change something. That's that kind of the math that is behind Le Chatelier's principle, I suppose. Okay, but the key thing you need to know: reaction quotient is at any point in time, Kc is equilibrium. Okay, this one was clearly a tough question which caught a lot of people out, really because you weren't that familiar with the idea of reaction quotient. It seemed to me, and I would encourage you. There's a nice little section in the CUP textbook on reaction quotient that I would really consider reading if you're not very confident on that. Not seen really very many questions on reaction quotient in papers, but it's definitely worth being aware of. So you know how to write the equation for reaction quotient, because it's the same as writing the reaction for the Kc equation. So SO3 squared over SO2 squared and O2 concentrations here. Okay. Stick the numbers in at the start. They're the concentrations given to you, or the volumes given to you at the start. Plug them in, you end up with a value for reaction quotient Q is equal to 0.500. One or two people try to give units for that. You don't need to give units for Kc or reaction quotient for the IB. All right? If the reaction quotient is less than Kc, the equilibrium will shift to the right in order to push the, in order to sort of meet or to gain equilibrium, return to equilibrium. And if the reaction quotient is greater than Kc, the reaction equilibrium will shift to the left. Okay, so that's a fact that you need to know. You can kind of work it out on the hoof if you can't remember it, if you think about it. But what needs to happen in order to get the number back to 282 or 0.282? Okay, the number needs to get smaller to get to 282. In order to get smaller, the equilibrium must shift to the left, or the reaction must proceed to the left. And by proceeding to the left, you make the denominators bigger. Simple as that, really. So, in other words, to get the mark, you needed to first of all work out the reaction quotient at the initial point, and then you have to say for the second mark, the reaction will shift to the left because Q at this time point is greater than Kc. That's for the second mark. Okay, so we spent quite a long time on the question, but it's worth having a little read up if you're not confident on the whole concept of Q. Right. Deduce giving a reason the effective increase in temperature on the concentration of N2O2. Right, when I marked this one, loads of you have learned Le Chatelier's principle really well, and you know what's going on. You knew that the reaction, or most of you knew that the reaction is exothermic in the forward direction. You worked that out, and that's good. And therefore you said the reaction equilibrium shifted to the left. Okay, well done, no marks. The reason you got no marks is because it asks you what the effect is on the concentration of N2O2. So it's all about exam technique here. You need to think about what it's asking you, and you've got to say that the concentration of N2O2 goes down. So there's no problems with your knowledge there, your theory, it's just reading the question. But you also have to give a reason. All you have to say is that because the reaction is exothermic, the forward reaction is exothermic. That will do nicely. Okay, the rest of question 6 is over here, and there's some tricky questions here, I think. Okay. So, right, you're told there's a reaction which involves the formation of NO2 from NO, and that obviously involves the addition of oxygen. And it proposes a mechanism for that, where you've got 2 lots of nitrogen oxide turn into this intermediate N2O2, which then gets oxidized with oxygen to 2 lots of NO2. Now, because the intermediate N2O2 is used up, it won't appear as one of the reactants, and it won't appear in the overall equation. I've written the overall equation here to help you understand what's going on. The N2O2 is simply an intermediate, and so it's not going to appear in the rate equation, the overall weight rate equation. What you've figured out, most of you, is that the second step is slow, so that's the rate determining step, and that's the one which therefore determines the rate equation. And because O2 is one of the reactants in the overall equation, and it's used once in the rate determining steps, it's unimolecular, well, it's first order rather with respect to oxygen, that must be in the rate equation to the power of 1. So that's in there, and lots of you got that right. But lots of you wanted to include N2O2 in the rate equation, but that's not one of the reactants. Okay, it's the intermediate, and N2O2 comes from the fast formate, or comes from 2 NOs coming together rapidly to form N2O2. So those must both be in the rate equation as well. So this would be regarded as a trimolecular reaction, where these 2 come together and then a third molecule comes together, or these 2 come together to make that, then a third molecule comes along and reacts with that. So we need 2 NOs in the rate equation as well. There's some extra details there on how to work this out, which I wouldn't personally use and don't think it helps. But if you want to see the mark scheme, just download it. It's easy enough to find. But I'm happy enough with this explanation. It works for me, and I can get 2 marks. If you get the rate equation right, you get 2 marks. There are ways of picking up 1 mark by using the kind of complicated stuff in the mark scheme that you don't need. Okay. Question D caused a whole lot of panic. You saw activation energy, you thought, right, I need the Arrhenius equation, but there's kind of 3 forms of the Arrhenius equation in your data book, and you had a bit of a flap and you didn't know which ones to use. Now, we've not really practiced this very much, so I'm not surprised that most people struggled with this, and you don't see too many questions along these lines. The equation you need is this one. This one tells you what happens to the rates of 2 reactions, or 1 reaction at 2 different temperatures. Okay, so you've got temperature 1 and temperature 2, and if the same reaction's at temperature 1, you get rate 1 or rate constant 1, and if the reaction's happening at temperature 2, you get rate constant 2. So all you have to do is look up that and then plug in some numbers. Now, what numbers to plug in was also tricky. The rate constant doubles when temperatures increase. So the rate constant doubles, it means that K2 is, let's say, you can make up any number you want. So the lowest, at the first temperature, let's say it's a rate constant of 1, and at the second temperature, the higher temperature, it's got a rate constant of 2. It doesn't matter what random rate constants you use there, as long as K2 is twice K1, in which case K2 over K1 is always going to be 0.5. So ln K1 over K2 becomes ln 0.5. The activation energy is what we're trying to find out, so we'll rearrange to have that the subject to the equation shortly. R is the gas constant, which is in the data book, and then the equation 1 over T2 minus 1 over T1. The 2 temperatures in Kelvin, of course, are 298 and 308. So all you've got to do is, I haven't rearranged at this point, I just plugged in the numbers, so ln 0.5 is equal to EA over R, and then I've evaluated T1 over T2, take away T1 over, so 1 over T2, take away 1 over T1, that comes to minus 1.09 times 10 to the 4, if you use those temperatures in Kelvin. And then all you've got to do is rearrange it, really simple, that activation energy is equal to natural log of 0.5 times R over that number there, and that comes to 52,900 joules per mole, but I've turned it into kilojoules per mole because that's what we normally write activation energy in. And it tells you to in the question, so it's really worth checking the question to make sure you've done it right. And that's that one.